Right, good morning everybody. Welcome to day 2 of the HPC AI Advisory Council Conference, the inaugural UK one. Thank you again to all the speakers from yesterday. Thank you in advance to all the speakers for today. So in a couple of minutes we'll be starting the programme of talks. And a big thank you to the sponsors who were on the screen, because obviously the sponsors have made it possible that this event could take place and that nobody had to be charged to attend. So we're very grateful for that and for their enthusiasm and support for the event. Gilad sends his regrets. He's had to leave early, so he won't be with us today, but he wanted to pass on his thanks to everybody for attending and for all the presentations and all the time that everybody has given up to both to be here and to present. One person I want to say a huge thank you to is Lisa Brandt. Many of you have had emails from her over the last weeks getting ready, so everything has been running smoothly thanks to all the running around that Lisa's been doing in the background, so thank you very much, Lisa. I'd also like to thank Michelle and the team here at College Court. This is the second conference they've run for us within a week, and they've done a fantastic job again, so if we could say thank you to them. And of course, thank you to Sydney Stevens. I'll thank her again at the end of the day, but Sydney has made sure that all of this happened and kept everything running for us. Many months we've been working on this together, so thank you, Sydney. A few housekeeping things that Sydney has told me to say. First of all, there are QR codes scattered around the room. That's for feedback. Please do whatever you do with QR codes and fill in whatever it leads you to. Secondly, in the afternoon, OCF have very kindly given up their sponsor slot to allow us to have a talk from Basil Alexandrov from the Hartree Centre, the Chief Scientist from the Hartree Centre. And so we'll be having that talk at 2:40 this afternoon. And finally, the raffle. In order to be in the raffle, I don't know what the prizes are, but you need to put your name badge or your business card in one of the buckets that's out on the desk outside, and you can only win if you're still here when the raffle takes place at the end of the day. So that's a good reason to hang around.
If I could just insert, I've been to a lot of these events. I've seen a lot of raffle prizes in my years on Earth. These are special. This is something special this time. You'll want to be here, you'll want to have a chance to win, you'll regret it if you're not, and you'll regret it forever. That's all I want to say, with no hyperbole at all.
So what I want is funding for the UKRI roadmap, so I'm hoping that's one of the prizes. Okay, so without any, there's no more announcements, so I'd like to ask Paul Calleja to come up and give his talk. So Paul has been at Cambridge for 13 years. Heading research computing there, and is involved in many projects we work. He's one of the service providers for DRAC, and we've worked very closely on many projects over that 13 years. So,
okay, thanks, Mark. Yeah, so
okay, thanks.
I'm really going to talk about the research computing service and the innovations we've been driving over 13 years now, and kind of like an incremental increase in complexity over those 13 years that have built quite a monster of a set of processes and people. And really this has all been aimed at driving UK research, programs. So it's a little bit of a retrospective, a little bit of where we are today and where things might be moving to in the future. So obviously Cambridge, I think, is well known to be one of the world's leading teaching and research institutions, but really with a heavy fixation on research, and the students really are just sausages to put into the research machine. Right, this is the purpose of students in Cambridge, so I'm told. But actually, I think even more interesting than the university is the technology cluster, the technology halo around the city, which has really grown up to be one of the most successful tech clusters in the world, certainly in Europe. And it's this interplay really between the technology parks and the university that make Cambridge such a vibrant place for technology innovation, and also means that you cannot buy a house within 15 miles of the centre of the city. It's just not possible anymore. So there's some infographics about the university. There's some interesting ones on here. This kind of 10,000 staff, 18,000 students ratio is an interesting ratio. Apparently this is not the case anymore. Apparently expenditure is higher than income, which is why the university is in this kind of austerity torpor. Not even Swan anymore in college, can you believe it? Or cheese. Cheese is off the menu because we were running a deficit. Oh, this is actually being recorded, I forgot about that. Okay. Remember, no more jokes about my employer. They might watch the video. Okay, so yeah, Cambridge, very interesting place, lots of Nobel Prizes, lots of staff, reasonable money. About 750,000, £250 million pounds of that is invested in research. That's quite a large research turnover. So this is the infographic on the science parks, 58,000 people, about 5,000 companies now, 12 billion, that number's increased. So it's a very active technology halo in Cambridge that of course feeds interactively with the university. So a lot of tech generation in Cambridge. So if you look at HPC, in Cambridge there's a 70-year pedigree, kind of history of HPC provision, right from the start at the beginning with EDSAC to what we're doing with OpenStack today. And this is quite an interesting picture. That's Maurice Wilkes there. EDSAC was one of the first machines with electronic lodestar memory. That's the memory there. It's a vat of mercury. They're all dead now, obviously. but quite interesting. And actually, they're recreating this now in Bletchley Park. So if you ever get the chance to go to Bletchley Park, there's a really interesting computer museum there, and they've got some of the seminal kind of historical machines. They are reconstructing this one now, I think, even with the vat of mercury, but not open like that. I think they've got it sealed. So this was the first machine that I installed in Cambridge 13 years ago. This was Intel Core Duo. So this is kind of like the last turn of the wheel when AMD were on top, but they then became not on top, and now they're coming back on top again. So this is quite an interesting kind of piece of history. This machine was when Intel got their mojo together with a chip design actually from Israel, which was that Core Duo. So that's actually quite interesting with our Mellanox hosts. But 13 years on top, I guess it's someone else's turn. So, and this is our current machine architecture, which we will go into in detail. And while we're talking about history, I had to put this slide up. I love this slide. This was the queue. So this is when spending a long time in the queue was really painful, and when users had a real reason to complain about the queues. Users don't know that they're born today, and they can still complain about the queue. This was the real queue. Stuart Rankin gave this talk the other day, and someone in the audience said, I was in that queue. There's still people alive that have stood and can attest to being in this queue. Apparently a bell would ring and your job's jammed. The job is this bit of paper going in there. Right. So users don't know how lucky they are when they complain about the queue. So over the last 13 years there's been a big transition really. This is what we kind of started off with 13 years ago. It's quite simple really, just one architecture, one cluster, one network, one bunch of spinning disk, and you could only consume it through Slurm. That was it, right? You take it or leave it. Today we have a much more complicated environment, which we'll go into in detail. So back when we started, we had 80 users, the normal suspects in physical sciences and astronomy, those big professors that bang their fists on the table and get the university to invest millions of pounds into their hobby. All internal users, £2 million of capital. It was actually the largest system in the UK. That was number 20 in the top 500 for £2 million. Can you imagine that? 2 million gave you 20 in the top 500 back then. 2 million won't even get you in the top 500 now. Right, so that's quite an interesting change. The amount of money people are investing in HPC systems has gone stratospheric, right? 20 million then got you number 20, 20 million now. Wouldn't make it in the list. 2 staff back then, 18 teraflops, hardly any storage. Storage was the money the money left over to change from spending flops we used to buy storage. Storage wasn't thought about 13 years ago. Only x86, all IB. Static, bare metal, Slurm. No automation really. We wind forward to today and it's a very different landscape. So 1,300 users, internal, kind of national service users, a lot of industry users. We have £22 million of capital in operation now. Still the largest system in the UK, interestingly. 30 staff, about 4 petaflops, lots more storage, a complete mix of technologies, and a much more kind of dynamic. We've moved to OpenStack, many access modes, high automation. So a real big transition in those 13 years. So when you look at our assets, what is research computing in Cambridge? Really, it's data center, it's people and processes, and it's systems. Obviously, the real value add comes in people and processes. The others are just necessities, really. And with time, we'll see more of this going into the cloud, I would think. This will still stay, but this will become a hybrid, on-prem, off-prem. Because it's just difficult to keep scaling this, right? This is a difficult function to scale. It needs a lot of upfront investment to scale the data center. So when you look at our team structure, we have around 30, this kind of goes up and down, but split across these kind of notional silos of, the typical user services, help desk, user support, platforms and system software. Although these teams are really merged now into one, it doesn't really help to keep those teams separate. A separate kind of innovation activity with staff that focus on innovation, not service. We have quite an active RSE team, scientific support team, and a specific activity around outreach, selling cycles to industry, and then a separate RSE effort just around genomics, because we have a big activity in genomics. Really, these two should be the same, but they're just separated. So the Cambridge model is quite odd. I wouldn't say it's a model that I would start again if I knew where it would lead to and the hassle it causes me. But it is a model. It works in Cambridge. So the real odd thing that drives all the other elements of the model is this, really, that we are 100% cost centre with zero funding from the university. Apart from my salary, they pay my salary. Nothing else do they pay. And I've just got a new associate director, Oz Parchment, and he says this causes perverse outcomes, this fact, in that it drives a particular way of working, which could look from certain elements of the university to quite an odd model. Right, so this 100% cost recovery model drives us to be kind of obviously quite outward looking, with a kind of an entrepreneurial attitude and a heavy customer focus. And by that I mean a paying customer focus. But the people that have the money get my attention for some odd reason. And people that don't have money think that's not good. But it just is the model. Yeah. So this leads us to be, all these things stem from this, that we are cross-council funded, we provide several national services, we have a strong industrial outreach activity, all again because of this key feature. We need diversity of revenue for growth and stability. Again, that feeds that diversity. We have our own kind of in-house system design, system integration, and support functions. Most of the systems we design and implement and support ourselves in a co-design process with industry. So we're very, very heavily into co-design, co-implement, co-support. It's the only way that we can keep our competitive edge. And that leads to a very strong vendor and supply chain partnership. So we have a very strong partnership with Dell, a very strong partnership with Dell supply chain, through interconnect with Mellanox, processors with Intel, ARM, AMD, NVIDIA. Because of course all the discounts you require don't come from the OEM, they come from the supply chain. Right, so you need that supply chain model. This is what I said before, we have a strong customer focus, stakeholder focus, rather than committee-based oversight. which I think is an anathema to sanity and my mental health. Right? Cambridge committees are. Let's not go there. So we have we rather focus on what our paying customers would want rather than some committee of self-opinionated people who just want to make my life a misery. Right. Growth is important for us, of course. We need to feed the beast, and we do that by continually growing. Without the growth, things would be awkward. Oz describes it as some kind of pyramid scam, but we just have to keep on growing, right? If we don't grow, I can't feed my employees. So growth is really essential to us. And the bottom, it's gone off the bottom here. So we're growing at about 25% compound annual growth rate every year in terms of users and revenue. So that's 25% growth for 13 years solid. System size, flops growth, as I was surprised when I did the spreadsheet yesterday, 50% a year in flops, 25% in staff and revenue. And that's how we keep feeding the beast. We just don't stand still. If we stand still, it will probably be an awkward story. But this is quite an odd model. I don't know other compute centres that have this model. It's just is the model we've fallen into. So I'm going to change tack now and talk about some technology things. So we have a really big push with OpenStack, and this is a really great collaboration with Stack HPC, and I think Stig was here yesterday. And there's Stig there, there's John Taylor, the CEO, and this is the CEO of the OpenStack Foundation when there was a Newton release, so we took him into a Cambridge library and got him an original manuscript of Principia Mathematica to hold. They even let him hold it without the gloves. So this was an interesting day, but we've got a very strong collaboration with John, and we've done a lot of work in the community driving this kind of convergence of OpenStack and HPC, and we've been working with John now for the Stack HPC for around 4 years with a lot of investments from the SKA, a lot of investments from Iris, a lot of investments from Dirac, all kind of leading into this state of affairs. And really, in essence, what you get with OpenStack is this ability to really kind of stratify your platform, and OpenStack enables you to use modern technologies for infrastructure provision. I'm no longer having to use 30-year-old scripts from the DOE, right? Which is, if you look at most HPC management stacks, it's 30-year-old scripts from the DOE. We're looking at, this technology is, ancient. But it hasn't, that whole world has not progressed, right, until now. So this gives us modern tools for infrastructure provision. And it allows you to separate things out into obviously infrastructure layer, a platform layer, and a science layer. And you can have different teams, not in the same organization, running those layers. So this is really what Iris is about. So Iris is about providing an infrastructure. So my team provide Iris infrastructure, and then other non-Cambridge teams provide the platform on that infrastructure and support that platform to its science base. So this is quite a strong concept, because normally in HPC the service provider has to do everything: infrastructure, platform and support. With this model, we can just provide the infrastructure, and we can let other third-party teams be responsible for the platform and the support of that platform, in a much more flexible way. That's going to be quite, I think, disruptive when that catches on, and you have those power groups, like your group, for example, would be one of those groups that would do that. Other groups that have that kind of infrastructure, that capability, would much rather run the platform and support it themselves. They don't want to be asked with the infrastructure, the machine room and the wires and the provisioning and the monitoring. So that's quite an interesting model. And so, of course, all these slides I shamelessly stole from John Taylor, by the way. So you might have seen them in his talk. And he gives a much better talk on this than I do. But this is all leading towards this concept of the software-defined supercomputer. Right? Everything is software-defined from and Stack HPC heavily use Ansible and containerization of the control plane. So with Ansible and these technologies, everything is software-defined from the original kind of setup, deployment of your control plane that's containerized. You deploy your infrastructure and your platform, and this is kind of a dynamic situation, right? So you can end up with a world where you can have kind of two modes of operation, really. You can have an OpenStack, on-prem virtualized infrastructure where you can provide these kind of silos of activity in a dynamic way. But if this virtualization layer bothers you, philosophically or performance-wise, you can just go bare metal. And this is really, most of our focus is, bare metal integration with OpenStack into different compute silos, which are separated from each other as separate tenant networks. Yeah, so this is a really powerful model of being able to deploy on an infrastructure dynamic research platforms. Yeah. And it kind of works, surprisingly. And we have one middleware layer for all of our needs. As a service provider, we can do everything we wish to do from this one technology solution. And I guess we've invested probably £1.5–2 million in this over 4 to 5 years to get to this state. And it's now becoming simple enough for non-rock stars to manage. Last year, the year before, you still need those rock star engineers that we can't afford or can't find. But it's becoming simpler, and I would think within 18 months time frame it will be relatively straightforward to deploy. Another thing you get with OpenStack, which is really interesting, is the monitoring and kind of log aggregation correlation function with this service called Monasca. And so this is really interesting. For free, of course, you can monitor all your different KPIs, different parameters. You have your log aggregation. All this goes into an ELK stack, which you can then correlate. So you can look at, I've got this error message happened at this time. What other log states were happening at that time? Normally, your system administrator has to use his own neural net to do that. Now you can do this within an environment and display it in very flexible ways with Grafana. And so this is a really powerful tool which we're working on with Stack HPC to provide canned views that mean something to a system administrator. And of course you can expose this to the users with their applications. So users can start to get this level of fine-grained activity on what's going on the system when they're running their job.
How deep is a scope can you get?
It goes,
retries in the network?
Yeah, you can go as deep as you want. Yeah, you can get everything. Of course, you need to work out, how am I going to store all this data? What's the granularity? But in theory, yes, everything is there, and it's in a very nicely presented form. You have to, of course, make the views. You can make any combination of anything you want. So what we're going to try to do is make things canned views of interest, but then allow power users like yourself the ability to go and make your own view with your own stats. Yeah, it's really powerful, and you get it for nothing with OpenStack. So I never have to look at a Nagios view ever again. Ganglia. Right. Why are people still using that stuff? I just don't get it. So now we'll seg into the system. So OpenStack really is one of the underlying technologies that drive our platform. And I think 3 years ago now, we decided to kind of change our architectural philosophy and really look to design a system that was focusing on this explosion of data, because we have seen across domains an explosion of data. The rise of AI, I'm only probably going to say that once in my talk. Only once. And so we wanted to build a system that had very high bandwidth storage, high bandwidth interconnect to the nodes, and would enable us on one platform to combine simulation with AI and data analytics in a single platform. And we call that the Cambridge Service for Data-Driven Discovery. Never let me name anything, it's an awful name, I hate it. But it's stuck now, I'm stuck with it. That's why all my children begin with A. Right. I wanted to number them, but my wife wouldn't let me. But yeah, that's the name. So this is the beast that is that service. And so this is a very complicated slide, but it kind of almost describes everything we do in Cambridge in one slide, which is kind of neat. So this is kind of the current platform here. Yes, I did get suckered into buying K&Ls, and yes, I am making Intel pay. So we have 340K. He's using them. He thinks they're great. He's my biggest K&L user. Yeah. But you're one of the few K&L users, obviously. When you're on them, I know when you're running, because that part of the data center overheats. This is how efficient. This is what efficiency means, right? This is why you know that most users' code is really woefully inefficient because there's no heat. But when he runs his job on the K&Ls, we get all these beeps go off. But it's the Peter beep. My sysadmins ignore it now. They're used to it. Oh, Peter's on again. The K&Ls are overheated. Anyway, so we have some K&Ls, some Hadoop infrastructure. We have actually a lot more Hadoop. We have around 350 nodes of Hadoop, but most of that is a private infrastructure for the Gaia satellite guys, with 87 for general usage. 360 NVIDIA P100s, lots of Intel Skylake cores. And this is kind of jointly funded by the university, by EDSAC Tier 2, Dirac, and Iris. But mainly, actually, our biggest funder at the moment now is Dirac. So Dirac are the largest stakeholder in terms of monetary value of that equipment. It's interesting, thank you, Mark. And this is probably what we're going to be expanding this year. So this year we should be expanding another 576 cores of 56 core Intel and a whole load of NVIDIA Volta Next PCI cards. So this is, obviously there's a very interesting market dynamics going on at the moment with AMD coming back after 13 years absence. That is driving significant competition in the market again. And that's all I'll say on camera, obviously. But this is good for us. Competition is a good thing. And NVIDIA are obviously responding with their next generation equipment, which is providing really interesting performance per watt increases, almost a factor 4. So the new NVIDIA cards will be almost twice as fast at almost half the power. Yeah, and with this you can start to really build pre-exascale prototypes. So I did a calculation the other day. So we'll be buying a 2U Dell AMD server. In that server we'll put 4 of these new NVIDIA cards and 2 Mellanox HDR200s. And with that you can be building an exaflop on 23 megawatts, which is actually, within range. This is kind of thing people need. And we'll be deploying 3 petaflops in 5 racks at under 100 kilowatts, which is pretty phenomenal, and under £2 million, which is actually quite phenomenal that you can get 3 petaflops in 5 racks for under £2 million. This is pretty interesting technology, and this is I think will be the first instantiation of a pre-exascale prototype. That doesn't come out in the market until July next year. Okay, so that's hardware layout. This is kind of quite interesting. We'll talk about this kind of storage layout with kind of solid state NVMe, Lustre and tape, and we've done a lot of work in how we move data between Lustre and NVMe. That's actually quite interesting, and that was funded again by Dirac mainly. A little bit EDSAC, a little bit university, but that was mainly a Dirac push. That was your discussion that sparked that whole project actually. This is quite interesting. Our network is a monster, is a kind of Frankenstein network of all kinds of technologies. Various generations of Mellanox. I was also suckered into OPA. I am a sucker for those Intel guys. That's twice they stung me. Don't worry, the Israelis have made me pay for that mistake. That was not my best moment. But anyway, OPA is good enough. That's what I say. It's good enough and it's cheap. But we will be rejoining the Mellanox fold. This will be our last kind of OPA expansion, because I have to sweat this asset. We have a big OPA asset. It's cheap. I'll sweat that asset here with these cores. We migrate here to Mellanox's latest technology, and probably after that it will all be Mellanox unless something else comes along. And so the network is a real mismatch, and the only way we make it work is with lots of routers. So we have lots of servers with multiple network cards in routing traffic between this network, and that there are many, how can I put it? undiagnosed performance features that happen here. Right, this is not, it all looks ideal on a diagram, but it works, but there are there are funny issues sometimes with the routers that we never really understand because it's very complicated. And a one-off because of our configuration. I'd much rather move to a more homogeneous network with time. But this is one of the problems when you evolve a platform over the years and you run it as a single system, you're bound to have a mismatch of technologies here. So on top of that, to glue it all together, we have our OpenStack layer. And that enables us to have a really kind of rich user access layer. So how do the users get access to this technology? They can do this one. So we can just use OpenStack to provide a single monolithic bare metal cluster with Slurm, just the same as it was before. The users see no difference. The only difference here is the tools that are provisioning this and monitoring this are modern tools and not 40-year-old technology from the DOE. So no one sees any difference apart from my system people. We can offer bare metal as a service, so customizable bare metal clusters just for you or your community. That's actually quite interesting, and we've done that with Iris for the Euclid community. They loved that. I've got a slide on that later which we can talk about. You can have a virtualized HPC infrastructure where your users are gaining access for a virtual layer. We do that in clinical school. You can deploy, infrastructure via Kubernetes, Jupyter Notebook on top of Kubernetes in a more kind of dynamic infrastructure. That's also interesting. You can just provide flat infrastructure as a service like you get from Amazon for people that want long-lived infrastructure. You have a research group that want to stand up their own, I don't know, it's quite common for web services. They have some data. They want to make that available to their community. They don't want to go and buy their own servers and plug it in their machine room. They want some long-lived infrastructure for their group. They can just buy that from us under a long-term kind of lease, a year, 2 years. We can wrap up various kind of data analytics or AI services. We're looking at wrapping up Hadoop within this, so we can give stakeholders their own Hadoop cluster, because Hadoop has many. If you're trying to use Hadoop in a shared mode with different stakeholders on one Hadoop infrastructure, there's very many nasty security loopholes that could mean data can leak between stakeholders. Hadoop is not designed really very well for a multi-user environment. But if you wrap up separate Hadoop instances within its own tenancy, you get away from that problem. We have a whole range of storage services. We're starting to do some collaboration with TAC in Austin around scientific gateways and an API that they've developed there for creating, application-centered views on the system. And the first thing we're going to do there is work with our cryo-EM community and try to produce a kind of a workflow controlled way for them to access the cluster. Because cryo-EM people are biologists. I was a biologist, and as a biologist you think of a workflow like you're standing at the lab, in the lab. And when you're in the lab you do things one at a time, manually. And that's how cryo-EM people think about their workflow. It's not the best when it comes to computing. They can do parallelization goes 2, because they've got 2 hands, right? They can't think of more than that. So we want to wrap up a workflow for the cryo-EM community, because the cryo-EM people actually can really utilize the KNLs, funnily enough. Quite a lot of this architecture, but they need helping. So scientific gateways where you wrap up workflows and applications for a particular community are quite interesting. We're also looking at just vanilla kind of HPC portals to enable, again, new users not to have to deal with a command prompt. So we're starting to do a lot of work in clinical medicine for the brain imaging center, and there are a lot of psychologists that want to get access to the infrastructure. I think if Stuart has to give one more Unix course to those psychologists, he's going to kill someone. So we really need not to have to do that. It's dangerous. So again, if we can give people, if we can abstract that away from people, it's all good, right? And the last one, which looks really small and insignificant, was really awkward. So we now have an ISO 27001 certification on all of this equipment, and we can offer a secure compute and data service. But this was a really difficult and long undertaking. I think it's taken us 2 years. It must have sucked in around 300 grand's worth of effort to do this, but it's useful, of course, because it unlocks a whole load of research projects in engineering, defence, social sciences, medicine. There's a lot of types of research that you need to be able to demonstrate you've got some security of the data and the people and the process. It's all people and processes, actually, it's not technical. And then obviously we have a layer of kind of business development, user support, RSE, a people layer. And that's actually where most of those 30 people, half are here and half are here in the platforms. So we have quite a rich biz dev, user support, RSE layer. And then you can gain access to these resources in a number of services. So we have our internal Cambridge service. We have our EDSAC Tier 2 national service. We have our DIRAC service. We have our IRIS service. We have a whole lot of innovation activity. Some of it is sponsored directly by Dell and Intel, some of it not. And then we have 2 limited companies, one for selling cycles to industry and one for selling consultancy and system integration services. This is quite new. This is reasonably old. And that's kind of everything we do on a page. Okay. We'll just talk about some of the things we do with this now. So the Data Accelerator is an interesting project that I say was born out of a conversation with Mark on potential requirements from your Gaia community. I think is what stimulated this idea and gave us some of the seed funding, because of course all our development work is normally leveraged off of production requirements. So we have a research community that have a requirement. It might be a new requirement, it's quite innovative requirement, and therefore we use that funding to try to develop innovative technologies. We don't have funding purely for innovation's sake. So normally we need a stakeholder that wants to push the envelope in a certain direction, and we use that stakeholder's kind of requirements to drive the innovation. And so it's normally the things we innovate on are very user focused, because the user is paying for them because he has a science need. That will be changing actually. Now we're going to start to get funding directly for innovation's sake, which is going to be interesting. So this actually, funnily enough, let me describe what it is. So sorry, we have one Dell server. These are Dell R740XDs. They have a lot of internal bandwidth. We have 24 of these servers. Each one of those servers has got 12 Intel NVMe drives, and that's all connected with OPA. But we spread out across the OPA network. It really doesn't work well if you try to concentrate those servers onto one OPA switch. It should do, in theory. There's no reason why it shouldn't, but it just doesn't work if you do that. There's undiagnosed congestion if we don't spread them out across the network. Okay, so 24 servers, each server with 12 NVMEs. We have 500 terabytes of usable storage. And when we configure that with Lustre, it's currently today the fastest storage solution in the world, as ranked by the IO 500. So this is a very interesting IO-focused benchmark. And this graph here shows you the position in the list over the last few years. And so you can see normally there's been a kind of slow kind of increment like this. This is Summit, a very expensive system in the States, with IBM Spectrum Scale, and there's us. So that was quite an interesting leap forward in twice the performance of the second place, and almost 4x over the rest of the field. This was quite an inflammatory slide I put on my LinkedIn, and I got quite a lot of. The storage community is quite an odd community, if ever you've played in there. It's much odder than the interconnect community. And it's very easy to inflame them. With slides like this. My LinkedIn was burning with comments from certain places. And this is why I did that, for a bit of fun. But it's actually quite interesting. So we get 500 gigabytes a second read. It's 97% efficiency on the reads. 340 gigabytes a second write. Obviously the NVMEs are very lopsided in their read-write performance, so this carries through in the specs. But the interesting thing is how much we're getting out. So this is expressed as the raw performance you get from one disk, right? And then up through the parallel file system and out across the network, we're getting 97% of that bandwidth. So the bandwidth efficiency is really good, right? Right? There's nothing more to squeeze there in efficiency. 28 million IOPS. So this is, quite shocking. And I'm not going to go into this too much now. We have a very detailed white paper that we've created with Dell that's going through its final last round of edits now. And this gives a kind of a high level overview of the work and a very detailed characterization of synthetic benchmarks. There is a companion Git repository which has all the detailed how-tos and scripts. So this whole thing is actually built with Ansible, and the feature which enables us to get that high performance, the kind of the trick, if you want to say that there's a trick, is that this is an ephemeral file system that's built on demand per job. So we need no resiliency or redundancy features that kill my performance. As soon as you put RAID across an NVMe file system, you can kiss your performance goodbye. Right? So with integration into Slurm and some software again written by SKA HPC by John Garbutt, who's an excellent engineer, we have a piece of software that interfaces with Slurm on the work that's already been done by Cray Data Warp. So we shim into Cray Data Warp, and on demand, a Lustre file system is laid out on the NVMe's per job. Data's copied onto that file system, calculations are done, data's written out, and then it's copied back to the spinning disk. So that's really powerful technique, because of course if we get an NVMe failure, it only brings down that one job. Yeah, and this is all described in the paper, and all the code and the Ansible scripts and everything you need to recreate this is in that GitHub. So these two things together, a reasonable Linux engineer that understands Lustre should be able to replicate what we've done. And this is just being made publicly available now. Right, so that's quite an interesting piece of work, and we can extend this. We intend to extend this for other file systems like PGFS, for example, for just NVMe over Fabrics. So you might not need a parallel file system at all, but again, on a per job basis, you will be able to stand up just a block of NVMEs directly attached to that server with no parallel file system in between. So there's lots of ways that you can take this. And really now, bandwidth and IOPS are fully determinant. It's just a function of how many NVMEs you have. It's fully determinant, and it doesn't get polluted by other jobs running on them because it's not shared. And so I/O becomes a determinant feature and no longer a problem. Okay, so another bit of innovation that we spent a lot of effort on. We have a large team, about 8 people, working on large-scale gene sequence analysis, and this is the only area really where we get involved in application development. So this is all funded by Genomics England, which is about to morph into the UK, what are they calling it now? The National Genome Interpretation Service. So there'll be kind of 8 regional genome sequencing centres taking a lot of sequences from routine clinical diagnostics in hospitals. So they'll all be feeding in to this software package, which is a kind of a next-gen sequence analysis piece of software developed by Ignino Macchio in my team. And it's really quite revolutionary in terms of the speed of the analysis that it does. And again, this is all open source, all described on the website. Okay. So one area that we spent a lot of time working toward in our OpenStack work and our ISO certification work was all really for this project, where at the hospital, obviously, you have the hospital network, which is relatively closed down, secure, controlled environment with all your kind of patient data. Then you have the university network, which is kind of the Wild West really, in terms of it's completely open and there's no consistent policy on firewalls or anything. It's just wild. And how do these two things come together? How do university staff interact with hospital staff and share data? Well, they can't. And so we created this kind of, an OpenStack sandbox that allows these two worlds to come together and hold data in an ISO accredited secure environment with airlocks moving data in and out. And this is just one example of some work actually that I was introduced by this guy, John Cromwell, at a Dell event. He's from Iowa. He's a surgeon. And he developed a statistical model for predicting whether a patient would get a post-operative infection. And he just runs a simple statistical model real time when the patient is in the theatre. He takes medical records, he takes some live telemetry data from the hospital, which is actually keyed in by the nurse that's doing the operation. He puts this into his statistical model, which is running live, and then he can predict whether that patient's liable to get an infection or not, and they change the procedure. And by doing this, he can cut post-op infections by 75%. This is huge. These are really expensive. I think he said that it's $30,000 is the additional cost, per patient for post-op. And so we set up a collaboration with this guy in the university in Cambridge to see if we can implement, some of these techniques for surgeries in the hospital. But there's loads of these. This is just one example. There's many, many, many low-hanging fruit in terms of real-time kind of analytics, and it's all quite simple stuff. Another kind of vanguard user of these services is the Wilson Brain Imaging Center, is what I was talking about before. So they do lots of brain scans. They have many, many clinicians, people out in the field running various applications on analyzing these brain scans. And they got a new machine. This is the machine. You put your head in that hole, and it makes this picture of your brain. And the data rates kind of went up phenomenally with these new machines. And of course, this is a common theme across science at the moment. People get new widgets. These new widgets produce loads more data at much higher data rates, and the old way that they did their compute doesn't work for them anymore. In microscopy, in cryo-EM, in imaging, across the field. It's the same in physics. And every field we're looking at, new experimental devices are producing data at 100x what they used to, and old ways of doing compute and data storage are no longer working. And so then a step function needs to come along. And this is what we did for these guys. And we encapsulate all their workflows in VMs, and they run VMs via Slurm. It's reasonably simple, and it works well for them. But they do find that a lot of their clinical users just can't deal with the Linux environment. And this is why we're trying to, again, encapsulate their workflows within a portal so that they don't have to understand Linux commands. We do a lot of work with the square kilometre array. The central data processor design team was led by Paul Alexander in Cambridge, and we've been doing a lot of work with Paul in kind of the HPC design elements. And again, this is where our relationship with Stack HPC started kind of 4 or 5 years ago. A lot of that work has been driven in collaboration with Stack HPC. And one of those pieces of work is this kind of, John's good at naming things, SKA Ala-SKA is a John invention. And this is their kind of performance prototype. It's an OpenStack system that has a whole load of really complex, the wiring. It doesn't really show here, but the wiring for that cluster is really complicated. Lots of different networks, lots of different storage, run as an OpenStack service for the application developers to try different things. This has been quite a success within the SKA community in driving their performance prototyping. This is something we spoke about earlier. This is the Euclid Slurm as a service. So this is my old machine. This was the Sandy Bridge. So this was a 6-year-old Intel cluster we were about to throw away. There's 9,000 cores of Sandy Bridge. Euclid come along saying they need a lot of compute and they need it in a hurry because they have some outputs that they needed to meet. And so under the Iris kind of stakeholder environment, we created a Slurm. We put OpenStack on all of this and managed to stand up a Slurm as a service just for Euclid, where they can import their whole way of working, which was quite specialized. And we could never do that on our vanilla, generic HPC cluster because it's just different, and Stuart wouldn't want to give them root anyway. And so we're having this normal discussion you have with users when they say they need root because they're special. And we have many special users in Cambridge, believe me. Really special ones. Really special ones. That's why I did put, I know, they know I think they're special. I love them all. This is why I have Oz Parchment now to talk to them for me. So the special ones do not have to deal with me anymore. I have someone to deal with the special ones. But anyway, we didn't have to have that discussion with the Euclid people because we could celebrate their specialness and give them their own Slurm as a service that's tailored to them. And this was a really successful, really to us, demonstrating how quickly we could stand this up on this infrastructure. And this is how things have progressed. We didn't need a team of rock stars for months to deploy the OpenStack on these nodes. It was relatively fast. John turned that around in a couple of weeks for Euclid, which is actually pretty impressive. So we're almost done. So this is one of our kind of user-facing activities that is sponsored by Dell and Intel. This is actually a really interesting activity for us. We have this kind of virtuous circle of technology providers, Dell, Intel, third-party providers, Mellanox, NVIDIA, whoever. Our kind of use case generation, our users, and kind of our HPC service provider knowledge. And we mix all that up in a pot. And we use that for driving activities, proof of concepts, kind of customer engagements, white papers. And we probably get around, I don't know, 25, 30 Dell customers through the door a year with different requirements, through this program. It's actually quite an interesting program for us because we don't have to go finding interesting customers to talk to Dell, bring them through the door. And it's actually quite a fruitful collaboration for us and for Dell. And we're kind of extending this philosophy now, not Dell Intel focused. So again, we have this same melting pot of technology providers, use cases, integration skills. This has got a hybrid funding model. It's funded from some money from UKRI, some money from the university, mostly money from industry. I think it's about 80% industry funded. We expect this to reach 10 FTE over the next 18 months. And we're going to be looking at a range of technologies. Okay, so this is a really interesting one, especially at this conference, this kind of emergence of RDMA Ethernet. Because obviously the interconnect market is also going through quite a consolidation, one could say. At the moment, there's really only one now, Mellanox, which will be absorbed into NVIDIA, which is interesting. And one is never good, right? We just don't like one. We love Mellanox, super, great, wonderful, but just one can only lead one way, right? Your prices can only go in one direction. And this is irritating. And so we need, as customers, need to drive competition. And I think competition is going to come in this space, in the RDMA Ethernet space. And that should be good for Mellanox because currently you are kings in there too. Right, so this is the area where we're going to see innovation and competition, I believe. And so we're trying to stimulate this market, this area. It's quite interesting what's happening there. Obviously, Intel have got a checkered HPC interconnect past. OPA is going nowhere, but they have made some interesting acquisitions with Barefoot Networks. So I think Ethernet is going to be quite interesting, all software defined. So I think here that the future is kind of software defined RDMA Ethernet. Look what Cray can do with that old third-hand Bristol technology. Mako, Quadrix, Nodal, Cray. Right? It's the same bloody IP. Yeah. My wife wouldn't let me buy it when Nodal went bust. Yeah, exactly. Right? So look what Cray can do. This is not rocket science really, and it's all there. So this is where I think we're going to get innovation. Next-gen file systems obviously is an area of interest. Intel Dios is quite an interesting technology. What else is coming along? How do we have file systems that are designed from the bottom up for solid-state storage? This is a very interesting area, so we'll be looking at this quite actively. This kind of domain-specific architectures is kind of, you have a chip for every different thing you do, right? So, this is quite interesting. Accelerators, GPUs, FPGAs, special AI silicon for your network is just going to be another domain-specific processor, right? That does networking, right? So this is what we're seeing: domain-specific processors for different functions that will spawn domain-specific languages to deal with them. So this is what the heterogeneous world I think is going to look like, right? Domain-specific architectures with their own languages controlled within some kind of OpenStack framework. This is quite interesting. Okay, obviously we're going to continue the work with OpenStack for HPC. There's still a lot to do there in terms of simplification, so you don't need the rockstar to make it work for you. This is an interesting one, which is completely invisible to most people. Software tools for managing a national infrastructure, which we in the UK do very badly. But there are some interesting products in the US. If you look at Exceed, you know, the Americans are great at spending money on all kinds of things, even here. So if you look at the amount of money the Exceed program has spent on things like XDMod and Open On Demand and ColdFront, they've put literally tens of millions of dollars, $20–25 million into software for helping you run a national infrastructure, allocations, you know, allocation control, monitoring, usage, impact, user access, accessibility. There's a whole load of tools. It's all open source. So we've started collaboration with those groups in the US. Most of this comes out of Buffalo and Ohio State. So there's two Buffalo. So one is XDMod, which is really rich for monitoring and impact analysis. The other main one is Open On Demand for user access, and ColdFront for allocations. And they have another group of packages around kind of managing wraps and things like that. The name eludes me. But we're going to start a collaboration with those two groups and bring that over to the UK and do some proof of concepts. Okay, and there's my last cryptic slide. What does that mean? Who can guess my pictogram? I had great fun making that pictogram. My boy got it. No one's going to get it, are they? My pictogram. So, HPC, the quiet revolution, is leading to an inflection point. Right? So this is it. We really are seeing some interesting things. So these numbers down here are equally cryptic, but so for 500K today, on current competitive pricing, you can get 96 nodes in 2 racks, given 250 teraflops, 1 petaflop, 1 petabyte of storage, 58 kilowatts. That's the cost per year. To do that 13 years ago would have cost me 31 million. Would have taken 8,000 nodes, 200 racks, 1.8 megawatts. This is a kind of revolution that's happened over the last 13 years that no one's really noticed, in a way. And HPC now is really accessible. I mean, the people like Peter will always be driving. You know, he'll never have enough. Right? The guys like that will never have enough. They'll always want the next biggest. He'll always want the machine that costs 31 million. But many people, many use cases, don't need that. And there are many use cases now where relatively modest chunks of HPC can make real life differences. You can design your boat, you can design your car, you can design your drug on relatively modest amounts of HPC. And this is a kind of a revolution that's going to really drive research computing. And I think there's going to be a difference between the Peters of this world that do HPC and the rest of us that do research computing. And it's that of course, the research computing of today is yesterday's HPC. So we need the kind of rock stars pushing the edge, but the kind of the follow-on technologies now are really accessible for many use domains, and that will give us the volume, which will drive your research. Will be the volume that you get from the people doing the everyday. And this trend, I think, is going to be accelerating because things are much more accessible now than they used to be. And the whole advent of cloud computing and people getting less precious about owning their data and the domains they put around their data is only going to accelerate this whole process. So I think the future is really interesting. And that is the end of the talk.